Welcome. We're going to be doing Physics 220, the LR time response lab. This lab we're going to be looking at a resistor and an inductor in series. The equipment for this lab is all contained in this clear box, and so we have these plugs which are all soldered to resistors here, and so the resistor values are labeled. And then there's also an inductor here. These are capacitors. We don't need to worry about those until the next lab, but there's an inductor here which has 63.8 millihenries of inductance. And then we also have this banana plug wire where we can choose whatever resistor we want to do for the lab. And so for this lab, we're going to go ahead and just do the big one, 695 ohm. And so it's connected all in series now. These two leads here, the red and the black, this is connected to the computer in which we have a computer program that's showing where we can waveform settings. We can adjust what is coming into the circuit, and so it's basically our computer is acting as a signal generator, and we control the wave type and the frequency that we're sending in via this program. And so another thing is to note is that this program is really cool because it also acts as an oscilloscope. So this yellow and green lead also feeds back to the computer, and if we put it over something, so if we put it over the whole circuit, we can see that it's the square wave, because this is what we sent the signal in. We want it to be a square wave frequency of 1,000 hertz, and we're looking at it now. That's it for the equipment portion of this lab, but the nice thing is that the first part of part A is actually looking at this precise lab, or this precise graph. And so this is real time. The input signal, which is what you should see for the number 1 box to the right of part A, it's a square wave that's being input. And so it's already sketched for you, but just to make sure just to verify that that is what's putting into the circuit, let's go ahead and go and measure over, I think it says the resistor first. So here we're measuring over that 695 ohm resistor. The oscilloscope leads are over that resistor, and we can see how the voltage responds. And so it has this cyclical kind of exponential like growth and decay. And if you need to pause it, I know you're supposed to sketch these, so if you need to pause it, go ahead and pause the video, or go back and pause the video so you can get a good sketch. But now we're over the inductor, so this is the last of the 3. We have the oscilloscope over the inductor, and we see these sharp rises and decays. And so that's the third plot that you need to worry about. And that's it for part A. Okay, so for part B, what we're going to do is we still have the same configuration, except now we're measuring over the resistor. I guess I can put it over here instead. We're measuring over the resistor of 695 ohms still. And so what we're going to do is try to find the time constant for this particular this particular LR circuit. And so we see the computer, similar to what we had before, right? We had that graph, and I'm going to go ahead and stop the data collection so that we see what's going on here. And so at the bottom of the graph, we're at 0, or pretty close to 0, maybe negative 0.01, right? And then at the top, one thing I should explain real quick is that this cursor is wherever the red lines intersect is showing the x and y coordinates at that intersection point. And so our x coordinate is time, okay, and then our y coordinate is voltage. And so what we want to do is find the time that it takes for the voltage to decay from its max, which is right about here. Okay, I would write down these two numbers, voltage, a time of 0.001224, and then a voltage of 1.87068 volts, okay? And so we want to find the time that it takes for that voltage to decay to 37% of its, there's approximately 37%-ish, right? About 37% of its max value, and the time, the difference in the x coordinate here, is the time constant, okay? And so what I'm going to do is, just so it's a little bit easier to see, I'm going to go ahead and just zoom in on the graph here. That's probably good enough. And so, I kind of know, do the math yourself, from those numbers that were previously given. Don't be afraid to rewind and go back and pause if you didn't get them. But I'm just gonna kind of sweep over the range, that 37% range, and then when you see the Y value, the voltage value that you calculated that it should be, go ahead and write down the X value. And it's okay if it's not, I know this is not the idealist situation to do this in. It's okay if it's not terribly precise, just do the best that you can. And so I'm going to start about here, 0.78, and so just watch those values as I try to go slow and as fine as possible. Okay, and I'll come back up. Again, just pause where it's closest to what it should be, and that the X value you can use to find the time that it took to decay. And so that's it for this resistor. Okay, so now for our second resistor, let's just go ahead and plug this here and move it up to the next highest one, which is 145 ohms. So we're still looking over the resistor, but this time it's 145 ohms. And if we look at the screen, one thing that you'll notice right off the bat is that there's not as much of that decay, right? It's not even getting all the way back down to 0 because it starts back up again. And so if you look at the equations in part A, you should be able to reason through why. But let's go ahead and try to find the time constant for this one as well. So one thing you'll note, like I said, so it's starting its max at about right there. So at 0.001022 seconds, and we're at 1.23138. You probably could be to 3 digits and still be fine, precision-wise. But that's where we're starting, and we're ending down here at about 0.29. And if this could keep going, it would go all the way down to 0. And so you could still use this value to 0 to find the time constant, or to find the 37%, what it should be, just because it doesn't get all the way to 0 before it starts back up again, but the time constant would be 37% of the time of the voltage from here to the 0 point. And so, yeah, so let's go ahead and sweep through. So try to do the calculation to find what it should be, and then I'll zoom in as well. Okay, here's a little bit easier to see kind of that exponential shape, but I'm going to go ahead and move down here closer to where it's going to be, and then try to go through as slowly as I can. Again, just do your best with pause and, give it your best shot. Okay, we're probably outside that range by now, so I'll just come back up. It doesn't have to be perfect, just do the best you can to get that value. But then that's going to be it for the lab. And those are the two time constants. It'd be helpful to think about why they're different, why changing the resistance affects it that way. You don't have to write about it for the lab sheet, but I think that would help you in understanding the circuit and this topic. But thanks for watching, and good luck with your final calculations there.